Gas X has the following properties. It's colorless, no effect on either red or blue litmus papers, no effect on lime water, flammable. All right. What is gas X? All right. So ammonia, we know, turns will turn red litmus paper blue, right? It's an alkaline gas. That's the test for it. Chlorine has a distinct yellow-green color. So I'll just write yellow. Yellow. Hydrogen is flammable, right? Hydrogen reacts with oxygen to produce water, and where you use hydrogen is two things come to mind in welding torches because it burns so well, and the other thing is it's used as rocket fuel because it again burns so well, right? Okay, the last one is oxygen. Could oxygen really be all four of these things, especially the last one? Is it not flammable? Well, if you think about what flammability is, it's something's ability to react with oxygen to, give an oxide, right? And also give off a lot of heat. That's what something, if something does that, it's flammable. That's what, it is. And that's a flame is a chemical reaction with oxygen. Fire is essentially something, or essentially something burning is something oxidizing with oxygen and giving off a lot of heat. So that's what you call. So oxygen itself is not flammable. So oxygen doesn't react with oxygen to, or it doesn't burn, right? Like it doesn't react with itself. So the answer they're looking for is D. Dilute sulfuric acid is electrolyzed between inert electrodes. So the electrodes aren't taking part in the reaction as opposed to electrodes like copper in the question we did a few videos ago, or like last year's exams. Which statement is correct? Hydrogen is released at the negative electrode. Let's figure it out. What set of ions are present? So you have sulfuric acid in the solution, and because it's a solution, it also has water. Now you have from the sulfuric acid, you're getting a lot of H plus ions and sulfate ions, right? And for H2O, you're getting again H plus ions and OH minus ions, right? What is happening now is that two of these will, between the two, hang on a second, where's my highlighter? Okay, so here are your anions, here are your cations. Cations will discharge at the cathode. So the negative electrode, the cations will discharge. So you have only one. Both sulfuric acid and hydrogen are producing H plus ions, which will discharge. So there's no competition. So at the cathode, H2 gas is produced because H plus reacts, gains electrons from the cathode, and hydrogen is produced, right? On the left hand side, you have the sulfate ion and the hydroxide ion. So on the list of cations, sorry, anions discharging, right? Sulfate is the most inert, whereas the hydroxide ion is way more easier to discharge. So over here, the OH ion discharges, right? The OH ion will discharge. Now the equation is very tricky for this. I asked people to memorize this because what happens is it discharges, it forms water, which you don't see produced because it's just all a solution of water, and a lot of oxygen is produced and a lot of electrons are given out, right? So if I try to balance this out, it's going to be 4 hydroxide ions, 2 over here, 2 over here, and 4 over here. Let's see if I have it balanced. No, I don't think so. I think I have too many oxygens. Let's erase that if I can. Oops. Plus just oxygen. and I think we're balanced. So oxygen will be produced at the anode over here, and hydrogen will be produced at the cathode. And essentially, you're taking away water from the solution because that's going away. And yeah, so let's see what the option says. Hydrogen is released at the negative electrode. Is that true? Yeah, that's true. Okay, oxygen is released at the positive electrode, and that's also true. Sulfur dioxide is released at the positive electrode. That's untrue. We already figured it out. Now, sulfate ions in a solution in electrolysis, they'll never be, uh, they never react, right? Because they're so inert compared to hydroxide ions. Because it's always in a solution. It's always more often than not the hydroxide ion discharging. The acid becomes more concentrated. I think they're right because the hydrogen is produced and the hydroxide ion is going away. So essentially these two are going away, leaving H plus and sulfuric acid behind. Well, this H plus, right? And it is getting more and more acidic because the water levels are decreasing in the same amount of sulfuric acid. So this is also true. So our answer is 1, 2, and 4. The answer is A. Which two substances are removed from the bottom of the blast furnace? Coke, carbon. Actually, coke isn't removed, it reacts, right? Coke will be the carbon that burns and turns into carbon dioxide, right? Oxidizing this, reducing this iron, right? And yeah, so coke is more likely used up. That's how you say it. Iron is produced and it is extracted from the bottom, right? Because iron's heavier, it sinks. Limestone is also used up, right? Limestone has calcium carbonate, which produces carbon dioxide, which helps with the process in the reaction. And also the calcium oxide also reacts with the silicon and other things to produce slag, which also gets removed from the bottom. So this is also from the bottom, whereas coke and the other two, coke and limestone, are used up, right? So the answer is 2 and 4. 2 and 4. It is D. The repeat unit of a polymer is shown. That's the repeat unit. Okay. Now by looking at it, it's one of those addition polymers. How do I know? Hey, I don't see any, ester linkages or amide linkages, as we call them. And just for revision, this is an ester linkage. It's an oxygen with a carbon, the double bonded O. That means an ester was present, an alcohol and acid was present, and they've joined together, forming this linkage over here. And the other one is the amide linkage, which is going to look a lot like, let's put it on top so it looks nicer. Kind of like that. Very similar, right? Very similar to each other. Let's just add more bonds to the top one as well. This is the link on top. Is the ester linkage. So polyesters will have them. Amide linkage, polyamides will have them. Right? Anyway, back to our question. Which monomer would produce this polymer? So it's taking a closer look at this. This opened up here. This is the repeating area, right? So there was an original double bond over here because it opened up like that, right? This opened up like that. So essentially we're looking for a carbon with a double bond. That's the center two carbons I drew. The left one has a CH3 and a hydrogen. The right one has a Cl and a bromine. See if we can find that. And this looks very similar to our answer. I think we already found it. This is don't worry too much about it, like, hey, that one is on top. Just think about it this way. Hey, it's just flipped, right? Yeah. Okay, so the same carbon has a CH3 and a hydrogen, and the other one has the two halogens on it, chlorine and bromine. I'm pretty sure A is our answer, but let's take a look at the other ones. This CH3 has a chlorine on it. I don't like that too much, right? Yeah, this wouldn't work because it should have a hydrogen. It should have a hydrogen where the CH3 is on that carbon. So this is out, definitely out. Okay, what about the next one? Same issue. It should have a hydrogen over here, and there's a bromine. You open this however way you want, you'll never get this. The placement, so the focus is the placement of these atoms, right? So you'll never get this again. C is out. And the last one is, I think the last one is just C, but reversed. Take a look at that. CH3 carbon bromine, CH3 carbon bromine. Look at that. It's just flipped. And the chlorine and hydrogen are also changing places, but they're identical. They're the same molecule, right? So that's out as well because we ruled out C. Same reason. So I was right. The correct answer is, look at that, A. Fossil fuels are used to power some internal combustion engines. Which pollutants are produced by internal combustion engine producing fossil fuels? So carbon dioxide we all know. From an incomplete combustion, this any engine will produce. Carbon monoxide, right? And nitrogen oxides, dioxide or monoxide is also produced because we have catalytic converters for this, right? To purify it, catalytic converters. And this is turning beyond the scope of the syllabus because it was never really highlighted, nor any books talk about it. But sometimes you'll have sulfur dioxide also being produced, which is, I believe, a very unfair question. Some diesel engines will have impure oils in it, which are not completely isolated from sulfur, right? Like you don't extract all the sulfur out of it. So they can, once the sulfur is there, normal engines won't. Your car probably doesn't if it doesn't take diesel if it's on petrol. But because it's pure, right? It's cleaned off. But some diesels will have it. So, I mean, why is this question even here? A very unfair question, but it can produce sulfur dioxide. So the correct answer is, shamefully, all three. Which statements about sulfur and its compounds are correct? Sulfur is in group 6 and of the group 6 of the periodic table and have 6 outer shell electrons. That's what being in group 6 means. You will have 6 electrons. That's correct. In hydrogen sulfide, now H2S, what does that remind you of? H2O, right? Dare I say. And this is oxygen is in group 6 as well. So the bonding in water is very similar to the bonding in hydrogen sulfide, how the electrons are arranged, the outer electrons, right? A spider just walked, like, can you say walked onto my iPad and I kind of flicked it and it yeeted off the table. I think I have a spider infestation. Anyway. The hydrogen sulfide H2S sulfur shares 1 electron with each hydrogen atom. Yeah, that's exactly true for water, so it's exactly true for H2S. Sulfur dioxide is used as a bleach. Now, the examiner reports us many people were not aware. I hope that wasn't the case when you guys were solving it, because sulfur dioxide is used as a bleach, mainly to, when you take wood to make paper, the wood is brown in color, so the sulfur dioxide bleaches it out. So you use it, and that's one major use of sulfur dioxide. It's used to make wood pulp white. So that's also true. So all 3 of these are true, and the correct answer is A. Alright, 50 centimeter cubes of 0.1 mole per decimeter cube of silver nitrate is added to 150 centimeter cube of 0.05 mole per decimeter cube of sodium chloride. So a solid silver chloride is produced because silver nitrate is actually a test for chlorides, right? it'll make AgCl. What is present in the beaker after the reaction has taken place? So like some or all of the silver and the chlorine has reacted. So we have to figure out what's in the beaker now. So here's my said beaker. Should cut down on the pizzas. Okay. You have 50 centimeter cube of 0.1 mole per decimeter cube. If I put the mole calculation in, let's figure out how many moles of it has. So it's 0.1 per decimeter cube, but you only have 0.05 decimeter cube of it. So it's as simple as 0.1 times 0.05, and you have silver nitrate is actually 0.005 moles worth of it, right? Simple equation. Concentration is equal to moles over volume. For the second one, you do the same thing, 0.05 times 0.150, and you get 0.0075. Now, how will this equation take place? Let's figure it out. Silver nitrate is AgNO3, which reacts with sodium chloride, mashallah, NaCl, and that gives me silver chloride, which is a solid, so it's not in the solution anymore. It's a solid, so it just turns into a solid. It's out of the solution. It's not dissolved into the solution. And the other thing it should give me is NaNO3, which is aqueous, because I'm looking at the answers and they're all aqueuses. Aqueuses. Aquae. Okay. Aquae. Right? So what's left in the solution? Now let's do the mole count again. I started with 0.005 moles and 0.0075. So I have sodium chloride in excess, right? So what's gonna happen is this reacts. How much will it react? So the ratio between them is 1 to 1, right? So 0.05 will react with 0.005 of this. I meant 0.005 for each counts to produce 0.005 and so on and so forth. But do you guys appreciate this is the limiting factor? This is less in quantity, right? So this will deplete completely and the reaction will stop then, but you'll have some amount of sodium chloride left in the solution. Does that make sense? How much exactly will it be left? If I make a line over here, this is what we had earlier. This is how we mixed it. This is how much got reacted. So the subtraction of these two numbers will let me know 0.0025 is left, right? This is also left, and this is marked in the question. And this is also present, right? Exactly 0.005 moles of it. So this is also there. So this is over here. This is accounted for over here. So this is gone. Like we'll just ignore this because they already accounted for this. And they're asking what else is left. So you'll have sodium nitrate produced. So that's in the solution over here. It's NaNO3. But you'll also have some unreacted sodium chloride as well, NaCl. So the answer is, I think B is highlighting. B, right? Oops. The answer is B. Let's take that away. I'll be that guy and say, you don't get enough mole questions, or not difficult ones. So yeah, so finally we have one. Nitrogen monoxide and oxygen react to form nitrogen dioxide. Right? What is the maximum volume of nitrogen dioxide that could be obtained when 1 decimeter cube of nitrogen monoxide reacts with 2 decimeter cube of oxygen? Now, one thing to note is that I could convert these into moles, but it's just a difference of 24, right? I'll have to divide this by 24 and multiply the value by 24. So what I can do is just use these values, right? So let's rewrite the equation down. It's 2NO reacting with O2, and notice how 2 amount of two reactants is given to us. So it's one of those limiting limiting reaction questions. What do I mean by limiting reactions? Let's say you have, 10 slices of toast and let's go with 10 patties, right? 10 shami kebabs. How many sandwiches can you make? And you realize that, okay, you need two slices and one kebab. I don't know, one kebab to make one sandwich, right? That's how it is. So if you have 10, and if you have 10 of this, you can actually make 5 sandwiches only because you're using 10 slices and 5 kebabs to make, right? And that's how it works. So the limiting reagent is you have more kebabs. That's not limiting your sandwich making. What's limiting is you don't have enough of these things, the slices. That's your limiting reactant, right? You don't have enough of this, so something else gets left behind. So if you want to calculate again how many sandwiches you can make, you can, okay, 10 will give me, 2 slices give me one sandwich, so 10 will give me. So you ignore the kebab count because they're in excess. That's the idea. So what is the maximum volume of nitrogen dioxide that could be obtained when 1 decimeter cube of nitrogen monoxide reacts with 2 decimeter cube? So they react in the ratio 2 to 1 to produce 2. And currently we have 1 decimeter cube of this to 2 decimeter cube of this, right? So how do we figure it out? So let's just keep nitrogen monoxide in account. 1 decimeter cube, right, will need 0.5 decimeter cube to produce 1 decimeter cube. That's the ratio, right? What I did was I just took nitrogen dioxide and figured out how much of each do I need, right? And that seems to happen. That's very plausible. I think I'll make 1 decimeter cube. Let's figure it out with the case of oxygen. And if I try to do that, how much do I have? I have 2 decimeter cube, which will require 4 decimeter cube of this. Look at that, greedy little. I don't have 4 decimeter cube. So this reaction will not take place when I think oxygen. So this is the excess amount, this is the limiting factor. So at most, this entirety will be used up, 1 decimeter cube of nitrogen monoxide reacting with 0.5 decimeter cube, only a small portion of what we have, because there's no more nitrogen monoxide to react more with the oxygen to produce more. So this is how the reaction will take place, right? So the answer is A. The energy profile diagram for the forward direction of a reversible reaction is shown. For the reverse reaction, which row correctly shows the sign of the activation energy and the type of enthalpy. So sign and type of enthalpy, right? So for the reverse reaction, you gotta understand, like, let's say this is the reaction. A is turning into B, right? If A is turning into B, A is the reactants, which is over here, and B is the product. The activation energy is from the reactant side to the peak, that's the activation energy, and the change in energy from A to B is the enthalpy change, right? Now the reverse reaction is going to be the exact opposite, right? It's actually, so you write it like this, like reversible, right? So what we're going to do is just separate it out and think about B is going back to A. So that's going to be the same graph. I'm trying my best to make this as with the same height possible. You start with B, which is roughly the same height, right? Same height, and it goes to the same peak, and it comes down back to where A is, right? That's the reverse reactions graph. Now you can, I'm just doing this to explain it better, but you can figure out going from here to here, right? But let me just finish my explanation. So what's going to be the activation energy over here? From the reactants to the peak is the activation energy for the reverse reaction, and it's still positive. The enthalpy change, or is negative because it's going down now because it's a reaction to products, right? So the same thing can be done over here because you realize that's your activation energy and this is your enthalpy change, right? And just to explain it better, I redrew it. So I hope you guys understand what's going on. But activation energy is positive on all accounts, and enthalpy change, so it's going down, it's negative, that's going to be exothermic. The correct answer is D. The formation of liquid water from hydrogen and oxygen may occur in 3 stages. So they divided the process up. What's happening is you have hydrogen gas and oxygen gas, and what's happening is, oh, like all the bonds are broken and it's just atoms of hydrogen and oxygen. Now these atoms now combine together to form gaseous, right? Gaseous water, and that water is cooling down to liquid water. So which of these is exothermic, or heat is given out, right? So bond breaking, bond being break, if you're breaking bonds, that's endothermic, right? That's endo. And bond formation, bonds forming, is exothermic. So where are bonds breaking and where are bonds forming? The first reaction is all bonds breaking. This is completely endo. And the second one is completely exothermic, right? Now, this is gaseous water turning into liquid water. It's not a chemical change, but it can be classified as heat given in and heat given out. So molecules in the gaseous state have enough energy to fight the atmosphere pressure and turn into a gas, right? That's what a gas is. Now when they cool down, or when that energy is taken away from them, they become more calm, sedated, right? And they turn into a liquid. So this is also an exothermic reaction, so to speak. And this is also exo, the heat is given out. So which stages would be exothermic? I'm gonna bet my chemistry it's C. In 4 separate experiments, 1, 2, 3, 4, nitric acid was added to excess marble chips and the volume of carbon dioxide formed was measured. So marble chips are calcium carbonate, and it's just an acid reaction taking place, right? Okay, in all 4 experiments, the same volume of nitric acid. So nitric acid is not being changed. The volume isn't being changed. Maybe the concentration is, because look at these graphs. Its concentration or temperature, or both concentration and temperature, were changed. The result of the experiment are shown below. So they're only changing the concentration, of nitric acid and the temperature, or both, right? Now, increasing the concentration also increases the number of moles of nitric acid used, right? So I'm going to guess this is with the higher concentration because you have more nitric acid, and this is with the lower concentration, right? This is with lower concentration, right? Now, taking a closer look with the same concentration, or like let's look at both have the same amount of higher concentration, but one is faster. I'm gonna say this is because temperature is higher for this one. Temperature is higher. Let's go with that. And over here, temperature is lower. Temperature is higher. You know, same thing. Which statement is correct? A lower concentration of acid was used in experiment 3 than in experiment 1. Lower concentration of acid was used. Okay, well, we have our answer. Kind of disappointing because I'm not too excited about the rest of the option. Experiment 4 was faster than experiment 3. Hell no. No, it wasn't, right? Look at it. 3 kind of finished in the 4-minute mark, where 4 finished at the 5.5 mark, so it wasn't slower. The other way around. The acid used in experiment 2 was lower concentration than that of 1. They both had the same concentration, right? The temperature of the acid was the same in experiments 1 and 2. No, the concentration was the same, and 1 and 3 had similar temperatures, but we don't know. You know, how can we tell? But yeah, so the A is our answer. Long question, very simple solution. Just had to read through it. Metals have a structure of positive ions in a sea of electrons. Metals are malleable because it is possible to force the ions to slide over each other. The alloy brass is blank malleable than pure copper than pure zinc. Less. It's less malleable. It is less malleable. Brass is blank to conduct electricity. Brass is still able to. Okay, so the answer is less and able. The answer is B. Now, why do you think brass is less malleable? Why is it more towards the brittle side than pure metals? Any alloy is less malleable, or like, you know, most alloys will be, because here's, let's say, metal. Here's metal 1 with, you know, some positively charged ions. I just won't draw too many. And here's metal B. They'll have a different size, so I'm just making B a lot larger, right? So the alloy of A and B, alloy is basically a mixture where brass is a mixture. So if you have A-B mixture, what you'll have is, you know, something like that. Actually, let's just remove this one and let's put this over. Some sort of mixture, right? Some sort of mixture. When you mix these two together and when they're stuck, now A's and B's on their own can easily slide over each other because they're the same size. Over here, when this gigantic thing tries to slide over, it kind of gets caught by the other ion. So this one gets caught because of this ion. It's not probably drawn the best way. So, but like with these irregular sizes of cations, it doesn't move as freely. So it makes the entire structure less malleable. So all alloys are naturally less malleable than their pure element counterparts. Which polymer contains only 3 different elements? Polymer contains 3 different elements. A protein, just by the link, has an H, there's no oxygen, oops, carbon, oh my god, right? That's the amide linkage, so it has 1, 2, 3, 4, at least 4 unique things. Polyethylene can have, you know, just 2. Here's an example of polyethylene where the hydrogens are hydrogens. And it keeps on going and going, right? Okay, polypropene will have just a CH3, but the elements are the same, right? Like, so if I want to make polypropene, here's polypropene. Something like that, right? Starch. Now, starch has, you know, carbon and hydrogen like a regular organic molecule. Then it's bonded to another starch molecule with a double bonded O, and so on and so forth. So this has only 3 different types. So in summary, you have 4, 2, 2, 3. Correct answer is D. The results of 2 tests of solutions X are shown. You're talking about sodium hydroxide and aqueous ammonia. The reactions if you have excess or just a few drops, like dilute or excess. Which ions present in the solution X? Now, this is one question which is salt analysis purely, and it's pure. This table is literally in every chemistry book. Like, it's one of those things. I know we haven't really, you know, spent too much time on it, but this table is literally in every chemistry book. Let's see if we can solve it. Let's try to zoom a bit. Okay, we can zoom. So the table is, you debate between, my color's gone. You debate between zinc ion, the aluminum ion, and the calcium ion. And you compare them. So you start with dilute NaOH. Shouldn't be zooming in. Dilute NaOH, then you have concentrated or excess NaOH, then you add NH3. Okay. And kind of like that. Okay, so what happens is when you add just a bit of NaOH, they all form a white precipitate. White precipitate, white precipitate. So you know it's one of the three when this happens with NaOH, right? Now, how do you tell the difference between the three? When you add excess NaOH, what happens is these two dissolve in excess. Okay, they'll dissolve and the precipitate, the powdery substance that forms, will go away. Over here, it just stays white precipitate for calcium. That's how you differentiate calcium from the rest. Like you throw a bit, okay, it's white, so it has to be zinc, aluminum, or calcium. When you throw a lot of in it, and if it doesn't dissolve, it's calcium, right? Now, how do you differentiate between zinc and aluminum? So when you add ammonia, ammonia will dissolve zinc, but it does not dissolve. Sorry, I think I used the wrong color. So much for that. This will dissolve, right? And this will give you a white precipitate, so you know the difference between the two. Okay, and there is no reaction over here, so it just doesn't really matter. Okay, that's how you separate all of them. So to figure out calcium, you just use excess NaOH, and to figure out the difference between zinc and aluminum, you just add ammonia and figure out which one gives you a precipitate. Note that ammonia is followed by NaOH, right? That's why it says dissolves. It'll dissolve the precipitate. Okay. Coming back here, aqueous sodium hydroxide gives a white precipitate to this unknown substance, and the precipitate dissolves. White precipitate, it dissolves in excess. So it's dissolved, it has to be either zinc or aluminum. Now, with ammonia, if it dissolves, it's going to be zinc in the next bit. So calcium's out, right? Because calcium doesn't dissolve, right? So it's going to be in the next round, if you add ammonia, I haven't seen it. If it dissolves in ammonia, it's going to be zinc. If it doesn't dissolve, it's going to be aluminum. So aqueous ammonia, when you add it, it's a white precipitate, which precipitate remains on excess. So it's gonna remain, so it's just gotta be, it's not shown like I move the table, but it's gotta be aluminium. Aluminium. And the secret for this question is you gotta know the table. Like how I do it is I have this table more or less memorized. There's a bit of logic to it, but it's essentially like it's kind of unfair, but you kind of need to know how each cations are reacting, and we can break it into parts like zinc, aluminum, and calcium. They kind of bundle up together. They have a very similar reaction, and yeah, that's how you do it. Which diagram shows the arrangement of particles inside a balloon containing a mixture of the gases nitrogen and oxygen? Okay, why did people think this was difficult? These are atoms. Nitrogen is actually diatomic, oxygen is diatomic. Over here, this looks like my answer. I think this is our answer. Over here, this also looks like our answer. Oh, okay, the difference is they're not mixed together where they will be mixed together. So, you know, diffusion and stuff. So this is our answer, actually. This looks more like it. And the last one, this is just nitrogen monoxide or something, right? This is one compound. So the correct answer is C. I think the reason why this question showed up is not because people were confused. I think just people were like, this is an easy question and B is the answer because like, hey, hello. And they just went with it without going through the rest of the options. So it's just one of those questions you don't want to, you're not even happy you got it right. A student follows the rate of the reaction between marble chips, calcium carbonate, and dilute hydrochloric acid. The reaction is shown below, and water and carbon dioxide is produced. What you essentially do is collect the carbon dioxide gas and check out how much you're collecting for each interval of time. So which diagram shows the apparatus that is suitable for this experiment? Can you figure out the rate of this reaction? You can do it here. This is kind of an unfair question because you don't normally collect carbon dioxide underwater because carbon dioxide dissolves in the water, but you can do it. You can collect it. For this situation, this is the ideal way of measuring it. This is the best way out of the four because the loose cotton plug allows the carbon dioxide to escape from the top, and it also prevents acid spills. Like when it's bubbling, there's no droplets coming out, and so it's a very safe way. And the loss in mass is observed here, and you can make a graph out of it. This is probably the best way. Over here, you can't really because there's no way to actually measure the how much gas is produced or how much the reaction is taking place. So you can't figure out the rate of reaction, right? Because you're probably the bottleneck by using a burette. Over here, the same experiment with a gas plug allows you to collect the gas over an interval of time and figure out how much volume you collected per time, per minute, and you can figure it out. So this is also doable. I think it's stupid, but it's doable. 4, 2, and 1 are kind of doable. So our option D is our best bet. Equal masses of methane gas are stored under different conditions. Under which set of conditions does the methane gas occupy the smallest volume? 0 degrees in atmospheric pressure, 0 degrees and twice atmospheric pressure. So cold and high pressure, higher pressure will compress the gas more, right? So the pressure outside is more, so like think about a balloon. First you cool it, it becomes smaller. Then you put it in a chamber which has more atmospheric pressure. So the bow of the, atmosphere is more. So it's like squeezing it even more. So B looks like our best bet. But like warmer at, so this is a win-win. 0 cooler is good, twice the atmospheric pressure is good. Over here you have twice the atmospheric pressure, but it's hotter, so it's not, still has energy to fight the atmospheric pressure. Let's think about it that way. And this is probably the worst in the situation. This is the maximum volume. So the correct answer, so the correct answer is B. Which statement is correct for all ionic compounds? They dissolve in water. No, they do not. Not all ionic compounds do. Case comes to mind where calcium carbonate is insoluble in water. Magnesium oxide, a lot of them aren't. Iron is insoluble in water. Rust, iron oxide. They are formed when metals share electrons with non-metals. It's not sharing, otherwise they're close, right? It's actually they donate it. Ionic is one way. Covalent is sharing. So like they give electrons. Metals will give their electrons to non-metals. They conduct electricity in the molten state. Isn't that true? Because the ions are free to move. That's true. They conduct electricity in the solid state. Not on my life. Nope. Nope. Because the ions are locked in place, cannot carry any electrons around. So the correct answer is C. The relativistic atomic mass of chlorine is 35.5. What is the mass of 2 moles of chlorine gas? 2 moles of chlorine gas. 1 atom of Cl is 35.5 grams. 1 molecule is actually Cl2, which is 2 atoms, which is going to be 71 grams. right? 1 mole of these things, right? So like, okay, anyway. What is the mass of 2 moles of chlorine gas? So if it's 2 moles of the molecule is the gas, right? This is Cl2. Oops. This is Cl2. So this is gonna be Cl2, which is actually 71 grams, multiply by like twice that amount, right? So that's gonna be 142 gramophones. It's D. The answer is D. When aqueous copper sulfate is electrolyzed using copper electrodes, which observations are correct? So what's happening is we need a electrolysis setup with like coppers. Now they're not inert electrodes, right? Inert electrodes are just fancy ways of saying electrodes aren't taking part in the reaction. Over here we've seen copper purification before, so they're just literally talking about that, right? So what happens to the two electrodes? So over here on the left hand side at the positive electrode or the anode, you have copper metal ready to lose electrons to form copper ions. So it's dissolving, the solid is turning into aqueous, so it's going to dissolve and produce electrons, right? So if this dissolves, this is going to get smaller and smaller because it's turning into the solution, it's dissolving. On the other side, it's going to get bigger and bigger because at the positive side, at the negative side, what's happening is the copper ions show up, grab a few electrons from the cathode, and stick to it, forming copper. Essentially purification of copper, because this would be the impure one, this would be the pure one collecting it. So the positive electrode will become smaller. I don't want to refute that statement. The negative electrode becomes bigger, and there's no gas given off because it's just that intensity of the blue colors remains constant because the amount of copper turning into the solution, going into the solution, which gives it its blue color, is actually the same amount of copper, coming out. Think of it this way. Copper gives away 2 electrons to turn into solution, so the solution becomes, slightly more blue because there's 1 more copper. Over here, another copper ion, the 2 plus ion, which already is making the solution blue, comes over here and finds those 2 electrons and picks them up and gets removed from the solution and turns into this metal over here, right? So whatever, because the electrons flow is balanced, whatever electrons are going from here are over here, the amount of copper produced over here is the same amount of copper removed here. The solution remains constant in color. And the answer is, what do I write? A. Under certain conditions, nitrogen reacts with oxygen to form N2O. And nitrogen, okay, reversible reaction, sure. The energy profile diagram is shown. What is the activation energy for the reverse reaction? So there are 2 ways of doing this. Either you can be, if you've done this question a few times, which I have a strong feeling you have, this is the activation energy for the reverse reaction. But if you're ever so confused, you can make another diagram for the reverse reaction. So the idea is for the reverse reaction, you start off from the products, which is N2O. You have the same, peak, and you go to the same place, same energy where you had the initial ingredients, right? And I won't balance it because I'm lazy. And the activation energy, you realize, if the highs are the same, you realize this value is going to be 447 minus 164. So that's just going to be very close to, I'm guessing, positive 283. I think that looks like a good answer. I think that's what it looks like if you subtract these 2 values together. An equilibrium question. Sulfur trioxide is produced by the following reaction. Which changes in condition would produce a greatest amount of sulfur trioxide at equilibrium? This is an exothermic reaction, all gases, more moles on the left hand side. Let's see. Adding a catalyst will change the rate of reaction of the forward and the backward one, keeping the equilibrium balanced. So increasing pressure is a good choice. Increasing pressure will favor the side with the least moles of gas, and because you have 3 moles for every 2 moles, for every 3 over here you have 2, because 2 and 1. You have increasing the pressure will favor this side and produce more SO3. More SO3, yay! Increasing the temperature. So increasing the temperature will favor the side which is producing less heat. So this is exothermic. Increasing the temperature will actually favor the backward reaction. Removing SO2 and O2. That will also, the equilibrium will try to balance itself and produce more SO2 and O2 and reduce the number of SO3. So yeah, increasing the pressure does it. The answer is B. Which change always occurs when a metal atom is oxidized? Oxidized is oxygen is loss of electrons, right? So if it's losing electrons, if a metal loses electrons, it's going to turn into at least one positive ion, right? So it becomes positively charged. Sounds like the correct answer. It doesn't have to be oxygen. Other things can oxidize as long as, the idea of oxidation is oil rig. If it's losing electrons, it's oxidizing. So you don't even have oxygen in the definition. It could be because of oxygen, but doesn't have to be just because of oxygen. If something loses electrons, it has been oxidized. It gains electrons, well, I'm going to ignore this. It gains a proton. Oh, I'm going to ignore this because protons do not change in chemistry. That's nuclear physics. This just does not happen. It's all about electrons in their valence shell, and that's all chemistry is, right? The answer is A. We're confident. Lock kar dein. Okay, which statement is correct? Which statement is correct? Hang on. Okay. Ammonia is produced when ammonium salt is formed with dilute acid. And that's weird. If I take ammonia out of it and if I say something is produced when a salt is reacted with an acid, isn't salt the product of an acid base reaction? So how could a salt, the product, react with more of the reactant? Like how could this happen? Wali baat na. So it would never produce the sa, as they say, or salt. Okay. Amphoteric oxides or oxides of certain metals, that's true. Aluminum comes to mind. They're all amphoteric, like it has to be a certain metal oxide to be amphoteric. A neutral solution does not contain hydroxide ions. Okay. A neutral solution contains equal amounts of H plus ions and hydroxide ions, right? Like water, which is neutral, has H plus ions present in it, but also has hydroxide ions present in it. Because they're in equal amounts, the acidity caused by the H plus ions and the basicity caused by the OH minus ions is negated, and the water is neutral. It's not that it doesn't contain it, it just contains it. It's in equal proportions. Even water has it. Soil with high pH can be neutralized by adding lime. Well, actually, it can be worsened. With low pH can be neutralized because this is alkaline. This is already higher, right? If this was low, that would be correct. So the correct answer right now is B. I'm going to go with A. Nitrogen as fertilizers can cause eutrophication to occur in rivers. Eutrophication is essentially you have nitrogen-based compounds in the fertilizer which can be washed away into the rivers and they'll settle somewhere in a lake or somewhere, right? And it causes a surge of plant life over there which depletes the oxygen in the lake, oxygen levels in the water, which causes all of them to die, and then increases the bacteria as well because there's a lot of dead plant, right? So first what's going to happen is the fertilizer, of course, will be washed into the river. That's the first step. Oxygen level becomes depleted in the river? No, Plants die, sure. Plants begin to decay. Plants in the river grow at an increase. So they, start going crazy. They start growing a lot. Then they'll die. Then they'll die. 3 for 3, right? And yeah. And when they die, they decay, well, obviously. And that's going to produce a lot of bacteria, which will suck up all the oxygen from the river, causing more death of different other life forms. So that's 5. Right, so in order is going to be 1, 5, 1, 5, sorry, 1, 5, 3, then 4, am I right? 4, then 2. 1, 5, 3, 4, 2. 1, 5, 4, 3, 4, 2. Answer is D. 3 suggested uses of sulfuric acids are listed. It is used as a battery acid. That's very common. Battery acid, yep. Battery. It's correct. To make ammonia from ammonium salts, ammonia is actually made from nitrogen in the atmosphere and hydrogen from cracking that's produced, right? And one reason I remember that is ammonia manufacturing plants are generally closer to petroleum plants, refineries, oil refineries. So they can easily collect the hydrogen from there and process it to make ammonia, which can make fertilizers. Sulfur, uric acid can also be used to make fertilizers with sulfates in them. So this is also correct. The correct answer is 1 and 3. C is the answer. The total number of electrons in one atom of element Q is 17. Number of electrons is 17. Okay, Q has 17 electrons, sure. And in one atom, the element R is 19. Okay, 19. Okay. Q and R react together to form a covalent compound. I guess this is more, they want us to open the periodic table. Okay, 17 electrons. They might be... Okay, they're talking about atoms, so I was confused. I thought they might be talking about ions. So 17 electrons in an atom means also 17 protons. We're talking about chlorine over here. And 19 is actually potassium. Okay. So Q and R react together to form a covalent compound. It's actually ionic, metal to a non-metal, potassium chloride. Q forms positive ions. Q actually forms negative ions, right? R has more outer shell electrons than Q. That's true. That has one more. R is more metallic than Q. That's also, I guess, true. R has more outer shell electrons. Oh, outer shell electrons. I just read this as has more outer shells. In the outer shell, potassium only has 1 electron. It's in group 1. This has 7. So chlorine actually has more outer shell electrons, more valence electrons. So this is incorrect. Premature, didn't really read the statement properly. But yeah, R is definitely a metal and chlorine Q is not. So D is the answer. Chlorofluorocarbon CFC compounds were used as aerosol propellants. The structure of one CFC compound is shown. Which element in this compound causes the depletion of the ozone in the atmosphere? It's chlorine. Chlorine does it. Cl. Answer is B. What is removed or destroyed when the water is desalinated? Desalinated. Desalinated. Desalined. Saline. What is saline solution? It's just salt water. What's salt? That's NaCl. So desalination is just removal of sodium chloride. You don't get enough organic questions. The structure of an ester is shown. This is ester. What is its name? Great question. So how we decide is between the carbon with the oxygen bonded to it, not this carbon, like the carbon with the oxygen double bonded to it, and the other oxygen, you break it apart. You cut it. because that's where they join together, you know? Okay. Because this is one carbon with the double bond, this is the acid part, and it only has one carbon, so this is methanoic acid. Methanoic acid. And on the other side, you have 3 carbons and an O, this is the alcohol part. So this is going to be propanol, prop, because of 3, and propanol, right? All because it's that, right? So the name of an ester is something aryl, something noate, right? Something aryl, something noate. That's how esters are named. The aryl comes from the alcohol. The noate comes from the acid, right? So this is propyl. That's the name coming from the alcohol. And methanoate. Methanoate. So oh my god, there's so many names, it's confusing. I suggest don't read the names before you attempt this question. Okay, what's the answer? Propyl, methanoate, metanoate. ठीक है. Answer is D.